Hello everyone, Mr. Hasty here. Today we're going to be talking about finding limits using your graphing calculator. We have a set of steps here. We're going to graph the function, whatever function we want to find the limit of. Then we're going to adjust our table set. We've probably never done this before, but you have a table function on your calculator and you can control how that works. You can choose where you start and what you go up and down by on the table. So where you start at is called your table start, and what you go up or down by is called your delta table, because remember, delta means change. So let's take a quick look at that. So let's look at the function x squared minus 5, just as an example. You can go ahead and graph that, and it's the parabola that we would expect. You can also go second table, and you see that you have an xy table. As you scroll up or down it, you can see values, but you can change where that table starts and what that table goes up or down by. So if you go to second table set, we can change our table start to 100 and our delta table to 2. Now if we go in there, wrong button, we'll see that we start at 100 and we go up or down by 2s. And for our purposes, where we want to look at really, really close values, we can set our delta table to be a specific value, 1, maybe, our table start. And then our delta table can be really, really small, like we can go up by 0.0001. And now when we look at it, we get all these values of -4. And the truth is that they're not all -4. That's the calculator rounding off decimal places. But we can see that everything around 1 is -4, leading us to assume that at the value of 1, we would get -4. And if we do the algebra, that checks out. So we're going to use this technology to solve some limit problems. All right, let's take a look at our first example. Here we have the limit as x approaches 3 of the function x minus 3 over x squared minus 5x plus 6. So we're going to use the graphing calculator to find this limit. As a note, it can also be done using algebra, which we'll learn to do later. So we're going to go in and we're going to plot that function, be x minus 3 divided by x squared minus 5x plus 6. Remember, the parentheses top and bottom are important here. If we look at the graph, it shows a hyperbolic function, similar to rational functions we've seen in the past. And if we try to trace it, click the trace button, you can end up getting close to 3 and kind of seeing what's going on. It looks like around 3, it's close to 0.97, 1.13, maybe it's even 1. But to know for sure, we have to get the table. So we go to our second table set, and we want to zoom in around 3. So our table start is 3, and our delta table, we need to be really close to 3, so our delta table has to be really small. Our table needs to go up and down from 3 only a little bit. So I'm going to use, let's see, 10th, 100th, 1000th, 10,000th, 100,000th, 100,000th. Now when we go to the table, it starts at 3 and it says error message because at 3 it's undefined. If we were to plug 3 in for real, it wouldn't work. And then we can scroll up and down. At 2.99999, we get a value of 1. Now it's not actually 1. If you look at the actual value, it's 1 point, what you see there. And if you go to the other side of it, it's not 3, it's 3.00001, and our value is not exactly 1 either, but the calculator has to round. But we can be pretty certain here that 3 is going to go to 1 in this case. So using our calculator, we're able to establish this is equal to 1. All right, on to example 2. So our example 2 is going to use a function that we might not have talked about in a little bit. We're going to use an absolute value function. we're going to the limit as x goes to 2 of the absolute value of x minus 2 over the quantity x minus 2. So when you typically have something on top and bottom, we think of it as coming out as 1. But the absolute value creates an odd behavior in the graph. So let's see it. I'm going to go to our graphing calculator and we're going to graph the absolute value of x minus 2. Double check our function here. Yep. Now, where's the absolute value? If you forgot, it's under the math button. And you can go over to the number menu. And the first one is ABS. That's your absolute value. The modern calculators will say, have the bars for the absolute value. The old school calculators will just have the word ABS and a parenthesis for you. So if we graph this, we can see what it looks like. It looks like a straight line that jumps to another straight line at 2. So going back to what we learned about limits and left and right hand limits, we have different left hand and right hand limits. And as long as it is accurate at 2, this limit should not exist. But let's double check. Get our table set. And we want to start at 2 because that's our target value. And again, we want a delta table that's really small. We go to look at the table. We get our error message at 2. And we can see at 2.00001, we have a value that is 1. And if we go up a little bit at 1.99999, we have a value of -1. So this indeed is a limit that does not exist because the left and the right do not agree in this case. That's why you always have to check above and below. So we would say that this limit does not exist, or D&E for short. All right, on to our third example. And for this one, we're going to look at a pretty useful and popular limit, one that comes up a lot in applications of limits to do derivatives. That's the limit as x goes to 0 of sine x over x. So we're using a trig function here. You will want to make sure your calculator is set to radian mode whenever you're working with graphs of trig functions. So going to our graphing calculator here, I'm going to clear and I'm going to do sine of x. Remember to close your parentheses. Divided by x. And also, I'm just going to take a second, go to mode and make sure I am in radian. And I am. So we're going to graph it, get what it looks like. So if we zoom in right here at 0, it looks like it's going through 1. But we know that can't be the case because if you were to put 0 into this, you would get a 0 in your denominator. That's undefined. So let's see what's really going on using our table. So because we're looking at 0, we're going to put 0 for our table start. And again, a delta table really, really small. I picked this value earlier, but it could be a different, very small value. It doesn't really matter. So we just need to be small enough that we can get a really good picture. So we go to our table set. And if we look here, instead of calling it 0, it calls 1e to the -5. That's scientific notation for 1 times 10 to the -5. And it says it's a value of 1. But if we look at it, it's not really a value of 1. It's a 0.9, so on and so forth. And if we go to the other side, because remember, you have to make sure both sides line up. Otherwise, you might have a does not exist situation. We have -1e to the -5. That's -1 times 10 to the -5. We also have a value really, really close to 1. And so that confirms here that the limit is 1. Okay. Moving on to problem 4, we're going to use a type of function you probably haven't seen in a bit. And that's a least integer function. You might have seen this in a couple different ways. I tend to write it like this with these lower bracket L's, and that means you're rounding down. You might have also seen it like this, or potentially just int of x, integer of x. So these create those stair-step equations. So let's take a look at this guy. So how do I even get a stair-step equation on this? If you go to math and you go to number down to int, and we're just looking at the integer of x, and we graph that, we get our stair-step. We're looking at it at 2, and of course we can see that at 2 is where it's stepping up to the next value. Sorry, if we look to the left of it, it's stepping down to 1. So what we're going to have here is we're probably going to have a does not exist limit, and that would make sense. But as we go to our table set, we're looking at the value of 2. And again, we want a really small delta table. We can see at 2, it has a value of 2. And slightly above 2, it has a value of 2. But slightly below 2, it would be rounded down to 1. It has a value of 1. And that confirms that this particular limit does not exist. So you have to check both sides of your table above and below in order to guarantee that the limit does in fact exist. All right, guys, that's our lesson for today. I'll see you on Monday.